Going to continue this idea of proof that we've been focusing on in chapter 2. And you'll notice the title also throws in this perpendicular concept that we've already explored, but we're just going to kind of throw out some more theorems actually. Now, so far, the proofs that we've done are what kind of proof, Mrs. Hochgravy?
They have been 2-column proofs because we've had our 1 column with all of our statements and 1 column with all of our reasons.
And it's, the 2 columns is very an easy way of organizing. It still has the logical argument kind of supported in there, right? You start with the given, you end with your proof. Well, what we're going to show you today is about another type of proof. Now, this is just another way of organizing the same information, all right? And the one that we don't ever really show you is a paragraph proof, and that's another organizational tool. All right, so a 2-column proof has the 2 columns. A flow proof, we're going to see that in a minute. And a paragraph would obviously be in a paragraph. Okay?
Which would make sense. It's really just reading your 2-column proof with all of the words that would be connecting. I know this because I know this.
Yeah.
And then I know this because I know that, because of this reason.
And I'll tell you, in college, most of the proofs I did had to be paragraph format. So we spend most of our time with 2-column just because it's a more kind of a basic proof.
And it's condensed.
And it's easy to kind of follow. All right. So the one that we show you, the one we're going to focus on kind of showing you today, is a flow proof. You will be asked to be able to do this on your own, but in the future, when it asks you to do a proof, we're not going to say, okay, you have to do 2-column, or you have to do a flow proof, or you have to do paragraph. You can make the call. All right.
Yeah.
On the classwork tomorrow, you're going to have to show us that you know how to do a flow proof, but in the future, you get a choice. Okay. So let's talk about it. A flow proof is a form of proof, like we said, and it says it uses arrows to show the flow of your logical argument. Okay, so the arrows are going to show you kind of how do I go from one place to the next, one statement to the next statement, right? It says each reason is written below the statement. So usually we see it statement
side by side.
Yeah, statement on the left, reason on the right. It says each statement is then also written in a box. So what we always did is we numbered the statements right underneath each other. With flow proof, you're going to see it in a box. And we're going to show you all of this here shortly. And then the whole idea of the arrow, it shows us the flow, all right, to the next statement. So it goes from one statement to the next. And then underneath, you're going to give, again, the reason is going to be written underneath. Notice right here it says the given information must be separated. Now, in a 2-column proof, we let you put it all in the first step. All right. With a flow proof, you need to separate because the statements that come from it might need to be separated for that reason. We'll talk about all of this when we do an example. All right.
So the first thing we're going to do is we are going to do a proof, just 2-column proof, the same way that we've done it before. And then we're going to do the exact same proof as a flow proof, just so you can see the difference between these 2 types of proofs. And you're going to notice that in Chapter 3, Mrs. Palermo and I are taking a shortcut. We're writing out the given statements already because hopefully by this point we've done a whole chapter with proof in it. You guys are comfortable knowing what that first step should always be, that it should always be our given information. So just because we write it out here does not mean that you don't write it.
Exactly.
You still need to have that in every proof that you're doing.
Yes.
So just something to be aware of. Okay. So in here they tell us that B is the midpoint of AC. So this point B is the midpoint of segment AC. And hopefully we're thinking what that tells us. And they tell us that C is the midpoint of BD. All right. That's all of our given information. And then we know that we're trying to prove some segments to be congruent. Now, Mrs. Palermo, just thinking off the top of your head, what does midpoint tell us?
All right, midpoint. I know a lot of us, in chapter 1 when we first heard about it, and we used it a lot in chapter 2, a lot of times you want to think middle point, but we know now, based on the definition, that midpoint means that it divides a segment into 2 congruent segments. So that means if B is the midpoint, that means segment AB and segment BC are congruent to each other.
All right, and notice I marked it in my picture, and now I'm going to write it down. We said segment AB is congruent to segment BC.
And notice it's not equal, all right? We've talked about this for a couple chapters now, talking about congruent segments. And that was because definition of midpoint. We've used this quite a bit over the last chapter with our proofs.
All right, and then, so we've used this step of our given. We haven't used the second step, but if C is the midpoint of BD, then that tells us that what?
That segment BC is congruent to segment CD. And I'm going to put it in the same step, if you're cool with that.
I'm cool with that. So BC is congruent to segment CD, and that reason is still because the definition of midpoint.
Exactly.
All right, so now we've used those two statements already, but we have some new statements that we've made. And they're both congruent statements, and what do you notice about them?
Well, I noticed they both have segment BC involved. So I know that then segment AB is congruent to segment CD. And that's because of transitive.
Yeah, and we've seen this a lot. When two things are congruent to the same thing, they're congruent to each other.
And that's it, right?
That is it. That's what they asked us to prove. Okay, we're going to do this exact same proof now as a flow proof.
So you already know kind of what the argument is. You have the information. So just kind of we decided we're not going to start a brand new proof. Okay, we're just going to show it in a different light. So the way the flow proof, I've seen flow proofs kind of go from top to bottom. I've seen flow proofs go left to right. So it just kind of depends on how much space you have. I'm going to go show this one top to bottom. Right, so you always start with the given, of course, and with a flow proof, let me kind of backtrack. With a flow proof, it said each statement is written in a box. So I'm going to take each of my statements. So one of the first statements I see is B is the midpoint, and I'm going to abbreviate some stuff, of segment AC. And I'm going to put it in like a little box, rectangle type thing. And underneath it, I'm going to put the reason, and the reason would be
Given.
So I'm going to put that right underneath. Now, notice I didn't put the other part of the given in the same box. It says that each given needs to be separated. So I'm going to put my other given information over here. All right, so if you wanted to go left to right, then you'd put it over here. But I'm going to go top to bottom just for room purposes here. So C is the midpoint of segment BD. Again, this should sound like deja vu because we just did this, but we're just showing you a different light. All right, so again, we already know, okay, well, B is the midpoint. Let's elaborate off of just this. If B is the midpoint of segment AC, this segment AC, what does that mean, Mrs. O'Grady?
We said that it forms two congruent segments, so that segment AB is congruent to segment BC.
So to show that flow, we're going to draw an arrow. So I'm going to draw an arrow, and I'm going to say exactly right, or write down exactly what Mrs. Hochgraby said. Segment AB is congruent to segment BC, and with the statement, I put the little box around it.
And then its reason goes below, right?
Yep.
So then below that, I would say that's the definition of midpoint.
All right.
Okay.
Now, before I go any further, because basically we can't really say anything off of that just yet, we need to go to this part of the given, and I'm going to draw an arrow to connect my next statement. And if C is the midpoint of segment BD, then what does that mean?
Then that means that segment BC is congruent to segment CD.
And again, put a little box around the statement. And the reason was?
Definition of midpoint.
And again, put the reason underneath. Again, that flow proof. So it goes from this, the given, and what does it mean next? There's the arrow to show it. Again, this reason, or this given, the arrow to show the flow, that connection in a sense. Now, from that, where did we go from there?
Well, from there, that's when we put those two statements together to use the transitive property.
So if they're going together...
Ooh, could we draw an arrow from each one of them to a new...
Excellent idea. Since we're needing both of them, I'm going to show an arrow to point to my next, and I'm going to do it from each of them. All right? So what did I conclude from both pieces here?
That segment AB was congruent to segment CD.
And I'll put the reason underneath, and that was
the transitive property.
Transitive property. So again, the whole idea of the flow proof is just to show that connection. If you look back at our 2-column, the information is exactly the same. It just has a different look.
Yeah.
This is flow proof. A lot of times is great for those that are more visual, kind of see that connection. Sometimes I know for myself, it's just a lot more writing, and there's the boxes. It takes a little longer for me to do, and it looks like it takes longer because look how much more space it is. So it's not something we're gonna do a lot in our class.
We won't model it a lot,
Yeah.
but if it helps you to do it that way, you're welcome.
We won't model it just because it's not necessarily my favorite type of proof, but that doesn't necessarily mean it's not yours. So you can use flow proof whenever if it makes more sense. But again, the big thing that's different about this is the fact that your given information has to be separate. All right, that's one big difference. No numbering of statements and reasons either.
All right, we've got a couple theorems to talk about. The next theorem, it's theorem 3.1 in our book. Notice that there's not a name that goes with this. When there is not a name that goes with our theorems, first of all, that means either we won't use it a ton or we'll just use kind of a short abbreviated statement of what it says.
So kind of explain it, like
Just
kind of
in a short
explain
description.
Short description. Okay.
Okay. And this theorem says that if two lines intersect, so if two lines are intersecting to form a linear pair of congruent angles. Ooh, let's think about that for a second. Linear pair, we know what that looks like, right?
Yep.
And we have learned a postulate with that, the linear pair postulate. So we know that that means that we have two angles that are going to add to equal 180 degrees, and they're congruent. So if they add to equal 180 and they're congruent,
Well, then that means they both have to be 90.
they both have to be 90, so then the lines are perpendicular.
Okay.
This is a very specific case. That's why we don't use it a ton.
Right.
But just realize that it's when we've got a linear pair of congruent angles that those lines will be perpendicular. And if I was to use this as a reason and a proof, that might be what I said. Linear pair of congruent angles, perpendicular lines, something of that nature.
Just
So-
kind of explaining it.
Just
in a sense.
explaining it in words, yeah.
Now, here's another theorem. Again, notice there's no name. It says if two sides of two adjacent acute angles are perpendicular. So there's kind of wordy. All right, so if we have two sides of two adjacent acute angles, let's just start there. So two sides of two adjacent. Now, we know adjacent means angles that are next to each other. They share a common side and vertex, but no common interior points. So in this picture, what are the two adjacent angles they're talking about?
Angle 1 and angle 2.
Angle 1 and angle 2. Notice they have to be acute, so that means that they have to be
less than
less
90.
than 90. And it says then what's going to happen is that they're going to be perpendicular. Now, what are they saying are perpendicular?
The two sides.
Are the two sides. So, in other words, in this picture, you would have to know that ray AC is perpendicular to ray AB first. Okay, so that's what they're saying. They're saying, what if this happens? All right, so if you have perpendicular rays that form a couple angles there, what's going to happen? Well, that means the angles that they're talking about are complementary. So if you know this, then what angles are going to be complementary?
That angle 1 and angle 2 will be
Are
complementary.
complementary. So I want you to think about this. Is this a logical theorem?
Yeah.
Right? Yeah. Well, because if this is going to be perpendicular, that means these two angles are going to, or this angle is going to be 90, right? Angle CAB is going to be 90, which means angle 1 and angle 2 are going to add up to 90, which means complementary.
Exactly.
So that's kind of what I kind of hit on was a semi-proof of this theorem, which we're going to actually do a proof of, I think, this theorem in a little bit. So I think we have one more theorem. Yep, here's one more.
All right. Now this theorem says that if two lines are perpendicular, then they intersect to form four right angles. We've actually already talked about what is the definition of something being perpendicular.
Well, definition
We
technically,
wouldn't say that it's the definition anymore, but this theorem just allows us to say, yeah, it could be any one of those angles because they are all going to be right angles. So if we know that two lines are perpendicular, if we know that R is, it's kind of a little tilted, R is perpendicular to Q, then I know that all four of these are right angles. It's not just one. So
Okay. So all angles are right, or all the angles are right angles.
You got it.